The normal way of detecting them is using some sort of sanitizer testing. Sanitizer will throw an error whenever such a memory error occurs. Now to the right you can see the same kind of bug, but this time the two variables are part of a struct user T, which might not feel different from a program logic perspective, but for the sanitizer it makes a huge difference, because most sanitizers only care about objects. The moment you put multiple fields in one struct, the sanitizer can't detect the error anymore. So the popular testing frameworks you might use when you are developing C and C++, for example AddressSanitizer, will only be able to detect the overflow on the left side, and the right one stays undetected. And the work we are doing helps us also detect the errors inside structs. As a small background for today, I will introduce compiler-based memory safety. Then we will talk about one type of sanitizer, which is the hardware-assisted AddressSanitizer. Then we will talk about the framework that we developed, and it's called Hardware-assisted AddressSanitizer with Intra-object detection, and short HWASanIO. And because we are really not we don't like to say it too often, we will just refer to it as Auer framework. Yeah. We will talk about the design, the implementation as part of the LLVM compiler framework, and the evaluation. So how is compiler-based memory safety developed in practice? So from a user perspective, the only thing you need to do is add a compiler flag, and then runtime checks are instrumented. For example, with Clang and GCC, you can use the fsanitize equals address or HW address, and you will get the corresponding sanitizer. The sanitizer will add instrumentation, and when the error is encountered during runtime, the program will crash with an error output. And in this case, we can see the error output of the AddressSanitizer. In this case, it encountered a stack buffer overflow, and it will give you the stack trace and also which part of your program is responsible for the memory error. Now there are some advantages. You don't need any changes to your source code, so you can do this automated, and your CI/CD pipeline will just tell you if there were any errors, for example. It can detect most of the common C and C++ memory errors, for example, out-of-bounds accesses and out-of-lifetime accesses. But there are some disadvantages. They have quite high amounts of overhead, so your program will slow down about 100%. That's mainly the reason why we use these sanitizers only during testing and not during runtime. And you also have some false negatives. Like I showed you before, the intra-object overflows are not detected by them. One example for a sanitizer is the hardware-assisted AddressSanitizer, and it's based on address tagging. So the tagging-based sanitizer uses a tag which is stored in the pointer variable and also in shadow memory. And then every time memory is accessed from a pointer, it will load the tag from shadow memory and compare it with the tag in the pointer, and then only allow the access if the tags match. So let's look at this in this figure. If we have allocated a buffer variable with 2 bytes, then we will get a pointer which has a tag set in its upper address bits, and also in the shadow memory belonging to the memory region. And the pointer is only allowed to access the data where the tag matches. Why is this hardware assisted? Well, the ARM top byte ignore feature is used, and basically that means that the pointer can have its upper tag bit set, and the load and store unit won't complain about an address translation error. Now this hardware-assisted AddressSanitizer was developed especially for embedded devices which are using the ARM architecture, and therefore one design goal was to keep the memory overhead quite low. So in this case it's only about 30%. And the way it is achieved is that it's using a 16:1 mapping, so every 16 bytes of data only has 1 byte of metadata. It can detect spatial and temporal memory violations, so out of bounds and out of lifetime accesses. The downsides are we only have 8 bits we can use for the tag, so at some point we will run out of different tags and we have to reuse them. And also we only have 1 tag per object. So if it's a struct, we can't detect any overflows between struct fields. Now our research question was, can we adapt this framework to enable efficient detection of intra-object overflows and underflows? And that's where I will present our framework. So the idea behind our framework is that we separate the tag, which is 8 bits, into 4 bits of color and 4 bits of shade. Now the color is used just as before to differentiate between objects, and it stays the same across an object. The second part, the shade, is used to differentiate between fields and members, and between each field and member it's incremented. So let's look at a small example. Here we have a struct which has 2 fields in it, 2 character buffers with 2 bytes each. Then we put some data in this struct and we place another variable just behind it. So the first struct will have the color part all set to the B value, which means that the tag stays the same across the object. But between the struct fields, so F1 and F2, we have different shades. So let's assume that we have an overflow in our program because we misused a pointer to this field. Then the moment we reach this second value, X, the shade is different and the program will crash. How is this done in practice? So the shade memory is set during allocation of objects, and then also the pointer values have to be shaded. And they are shaded dependent on the targets they address. So for example, if I create a pointer to the object itself, because it's the entire object, I don't need any shade value. The pointer would be allowed to access all of the members. Now, if I take a sub-pointer to the first field, then the shade will be set to 1, and the pointer will only be able to access the upper half of the struct. Another mechanism we have is that at some point we will run out of shade values. So if it has more than 2 to the power of 4 fields, and then we just start again at the 1 value. How can we use this framework? We added it as part of the LLVM compiler infrastructure. So just as you probably know, it has open source and reusable components, and it can be used as part of Clang. The pipeline, we have our traditional C and C++ program, which might have some memory bugs in it. We do our instrumentation, and after that the bugs become mitigated. As part of the framework, we have a new compiler runtime, which does the initialization of all the shading, metadata, and also initialization and function interception. Of course, you would expect that this added complexity will also lead to additional overhead, and that's why we added some new optimizations to keep the overhead low. For example, some pointers are only used for non-struct types, in this case, we only check the color part of the memory tag. Additionally, we added optimizations you can also find in other sanitizers. For example, in this picture on the right, you can see that the value variable is used multiple times in a row, so you only have to check if it's a valid memory address once, and then you can keep using the value without doing the check again. So we evaluated the framework looking at how efficient is it and how many bugs does it find. And to determine how many bugs we can find, we use the Juliet Test Suite, which contains a lot of different C and C++ programs with different kinds of weaknesses in them. They are sorted by the common weakness enumerator. For example, here you can find all the overflows for stack heap. We have underwrites, overreads, and also the temporal violations, for example, double free. When we compare the results of the traditional hardware-assisted address sanitizer, which is this one, you can see that it only detects about 85% of the test cases. Now for our framework, we actually managed to detect all of the test cases in the Juliet Test Suites. And this is also where we perform better than AddressSanitizer, because AddressSanitizer can't detect intra-object violations. Now that doesn't mean that we will always detect every bug in the wild, because we still have the small entropy due to the tag bits. So we only detect all over and underflows, but if you jump between different variables, then you might have a tag reuse and probably a false negative. When looking at the performance overhead, we measured it on an ARM device, the M2 MacBook, and we used the spec CPU benchmark. So as you can see, the blue values are the unmodified hardware-assisted address sanitizers. Orange is our framework. And for most test cases, you only see a small increase in the performance overhead. Now there's one exception, which is this image processing benchmark POF array. And there's a special case where the image processing needs to allocate a struct with a lot of different fields, and this leads to a very high overhead. Now we also evaluated the memory overhead. As I said before, this one was very low for the hardware-assisted address sanitizer. So in our version, only 35%. But we had to change the granularity from 16:1 to 1:1, which means that on average we are 100% points higher in the memory overhead. Again, there's a small outlier in the POF array, but for the rest of the benchmarks, you can see that it's about 100% overhead. So what was the goal and the results of the hardware-assisted address sanitizer with I/O detection? We wanted to fix the problem of current sanitizers where you have C and C++ code, which will probably use a lot of classes and structs, but then you can't detect them because your sanitizer doesn't have intra-object detection. So we added it to the hardware address sanitizer while keeping all of its others detection guarantees. It's usable as part of the Clang, so it can target all ARM devices which have this top byte ignore feature, and it's still only a small overhead, all things considered. Where are we going in the future? So of course we want to use this framework to detect real-world bugs, and there the best combination would be with a fuzzing setup. So the fuzzer will generate random input, and every time a bug is detected, you get the feedback. We also plan to upstream the source code to the LLVM repository, and then it would be easily usable for everyone who's using Clang to compile his C and C++ code. Thank you for listening today, and I would invite you to ask questions.
Okay, nice talk. Yeah, we have the first question.
Hi, so this looks really exciting. I guess I have a couple of questions. Did I understand correctly that when you use a zero tag, you can access the whole struct? Is that right?
Yeah, that's exactly right. So the reason is that in C and C++, often you will have void pointers. And for example, a function might use a void pointer to set an object to 0 across its whole size. And in this case, the pointer needs to access all parts of the object. And it doesn't know the type. So we have to have this magical 0 value, otherwise we wouldn't be able to support void pointers.
And I guess I'm wondering, kind of related to that, if you ever saw cases of false positives where someone took the address of a sub-object and then tried to use offset of tricks or things like that to go back into the struct. How common is that?
Yeah, that's also a good question. So some benchmarks, they use some kind of inheritance in C. And the way it works is that you have two structs which share the upper 5 fields, for example, and then the lower fields will be different. And I'm not sure if that's even legal C, but of course we can't support it anymore if the fields have different sizes. And also what sometimes happens is that inside a function someone will create a raw pointer from a variable and then later cast it to another type. And in this case we also lose the shade value. But for the benchmarks we evaluated in the spec CPU suite, we supported 16 out of 17 out of them.
Any other question?
Yeah, thanks. I'm wondering, have you tried how your sanitizer interacts with other sanitizers and whether you can run them at the same time? The one I'm particularly curious about, I guess, is HWASan, is whether your sanitizer interacts well with that.
So I know that AddressSanitizer and HWASan, they work together, and I'm not sure if the Hardware-assisted by default works together with it, but I don't think that we changed this part of the sanitizer. So if it worked before, then it should still work now.
Very quick question.
If you go back to your table, I got the impression that some of the benefits were coming on property on sort of overflows that were not intra-object. Am I misreading that? Like Stack Overflow, what's going on there?
That's an excellent point. So in my opinion, the default implementation of the hardware-assisted AddressSanitizer doesn't detect all over and underflows. It would detect. And one reason is that when they allocate a new object, they just give it a random tag, and that might collide with the object before and after. So what we did is we added a check that when a new object is allocated, it has to have a different tag value than the object before and after. So that's the difference to the 100%. And as you can see, we also improved the temporal detection, so the the use after free, for example, there are the AddressSanitizer also negatives.
Okay, we are at time, so let's thank Konrad again. Thank you.